NVIS, near vertical incidence Skywave. Maybe. There we go. So I didn't put anything fancy here together. So what is NVIS? It's a communication method, bridging the gap between local line of sight communication and DX communication. We are trying to provide regional coverage within your average skip zone. So think about it this way, with a handheld, the repeater, you can talk pretty far, but again, it only goes so far because you've got a horizon coming up. With DX, you're trying to talk as far as you possibly can. You got that skip zone, you got the dead zone where you just can't hear anything. Like I was talking about with me with POTA, I could not hear the guys over in Mississippi. We were just too close together the way propagation worked. This is allowing us to try to make sure we can talk within that zone, because again, it's for regional communications, or in our case, with what the reason Aries is talking all about this, and I'm not an Aries representative, but I just think it's fascinating, is excellent for emergency communications. You want to be able to get information in and out of that region or within that region to emergency responders. And sometimes if your infrastructure is down, your repeaters aren't working, your HTs at 5 watts just aren't cutting it. So it's basically is Skywave propagation. As you see in the diagram there, your DX communication, your whole goal really is to try to get that 45-degree launch angle so you can get it to hit the ionosphere and bounce as far as you possibly can. With NVIS, what you're really trying to do is near vertical incidence. You're trying to get your signal aimed up as near to vertical as you can. That way it's going to come back down on you. As I always describe it, it's when you take a squirt gun over at the pool, aim it up in the air and you squirt it and it sprays down on yourself. That's exactly what we're trying to do. We're not trying to get the signal out far, trying to get it to come down locally like an umbrella. And the key right there is the launch elevation angles. You'll see the DX one, which is one further out, it has a lower angle. It's trying to get it closer to that radio horizon, that line going off in the distance, so we can get further out and get beyond our line of sight. With NVIS, we're not doing it. As will come into play later on, you'll see that we are concerned with our layers of the ionosphere. So again, there's really two components for success: propagation and antenna. Propagation is probably going to be the least thing that you have control over, but we'll talk about that, and then the antenna itself, which that when you have a lot of control over. So the frequency is key in this with the propagation. If you're too high, you're going to just pass right through the ionosphere and go straight out into space. If your frequency is too low, you're going to get absorbed by the D layer, and your signal's not going to go out anywhere. You're just warming up the ionosphere. And then just right, you want it to be reflected down. So you need to figure out what that key frequency is. And as I said here, we got the diagram again. D layer absorbs. It has a tendency it exists only during the day. It disappears very quickly at night. And that's one of those things, if you're working field day a really good example are the QSO parties. If you work the Ohio QSO party, all of a sudden you start hearing all these stations start appearing again because the D layer, as the sun goes down, disappears, it dissolves. It doesn't have enough UV to maintain itself. It has a tendency to block 5 megahertz and lower. So you see most of our band allocations are higher than that, but not all of them. And it also attenuates the 5 megahertz and 10 megahertz frequencies. The key to that one is when we're going through NVIS, we're going up through the D layer and then back down through the D layer, but we're short distance. If you take a look at the DX diagram, the DX arc there, you'll see that this is spending more time in the D layer, longer distance, more absorption. So it attenuates it, but we're still able to work it. So F layer refraction, there are 2 layers. Again, I don't know how many people know about propagation. This may be one of those things, do another deep dive into propagation. But you got the 2 layers, the F1 and the F2 layer. The F1 is during the day, wind, not winter. I don't know how to describe that any better. The F1 layer doesn't really appear too much in the winter, but it's in the daytime. And at night, the F1 and F2 combine because the F layer is completely driven by UV solar radiation. As soon as the sun goes down, the 2 layers begin to move to each other, become 1 layer. F2 is higher than the F1, which again is higher than the D. There's lots of different layers. Those are the kind of the 3 key. Don't worry about E. I didn't put anything about E in here. E can't come into play, but that's not too much to worry about. So MUF is the maximum usable frequency. That's what we're looking for. Maximum usable frequency is the maximum usable frequency to create a circuit between you and the location you're going to. So you'll hear people talk about critical frequency. The critical frequency, I had to look this one up. I'm like, wait, I thought the two were the same. They aren't. Critical frequency is basically the frequency that the ionosphere will reflect a signal at that frequency down. So you use an isonode to send up a signal and then come back down. And it finds that frequency. That's the one that's, once it won't come back that point, then that's that frequency. I didn't say that very well. When the signal is no longer bouncing back at you, that's your critical frequency. That's like, okay, if you go any higher, you're not going to get it. It's going out into space. MUF, though, is more dealing with how much you're spending time in there and refracting. So it's basically from location to location. So your MUF, I pull out my notes here. The MUF is path dependent, 3 to 5 times the critical frequency. So it's 3 times the critical frequency of the F layer. So the rule of thumb is going to be find out what your MUF is, and you can get these. This is all, you can find all these different MUFs from real-time isonodes and whatnot. 20% of the MUF frequency is the frequency you want to be at. Yes, technically it's 80%.
Changes with sunspots.
Yes, it changes with, well, yes, it does change with sunspots.
Goes higher.
Typically goes higher because the ionosphere is being absorbing more UV radiation. But it even is throughout the year it changes. As we get longer and longer days, the ionosphere above your QTH is getting more and more UV radiation. It's charging the ionosphere more and more. So you get the layers separate even more, that D layer builds up even more. And in the wintertime, you're not getting nearly as much. Same thing with and remember, it's different radiation. This is UV radiation. There's a lot of other radiations that are coming through that do impact that as well. So again, we're going to be looking for that MUF of the F layer in play. So if you're doing it at night, you're really thinking about your F2 layer. If it's during the day, you're really thinking about your F1 layer. So rules of thumb, you get 40 megahertz during the day or the afternoon, 80 megahertz afternoon, evening, and if you can do it, 160 megahertz evening, night. 160 megahertz does not go through the D layer at all. So don't even try when the D layer is up there. 40 meters is usually pretty good, but 80 meters is better at night. Again, that D layer starts going away and you get that maximum usable frequency is approaching a better for those frequencies. So that's a little bit about propagation, about what you're looking for. But the big thing, the next thing is going to be what you can control. That's your antenna. And the key is the height above ground. Remember, whenever we go through a lot of our antenna knowledge, we're trying to create DX antennas. We are trying to get that signal over to Europe. We're trying to work that DX of Asia or in Australia. So we're trying to get our signal to go as low across the horizon, strike that ionosphere, and then bounce down and try to get that single hop as far as we can get it to go. In this case, it's the opposite. We are trying to get low to the ground because, again, if you know your antenna modeling, and I'll show some models here in a little bit, the antenna modeling, you are, as you get closer and closer to the ground, more and more of the energy is aimed towards the direct vertical. So you're looking for 1/4 wavelength or less. Again, normally you're thinking half wavelength. So this is one of the nice things about this is these antennas are not that high. You can get some pretty reasonable antennas. Typically between 1/8 or 1/10 of a wavelength. So you can get these pretty low. One piece of help is a parasitic reflector. You can put a wire immediately underneath it, 5% longer. And now this one, the literature is different. I'll explain this in a minute. It's either 15 below, 15 hundredths of a wavelength below the driven antenna, or between 100th or 600th of a wavelength above the ground. This is ripe for experimentation. I've seen people who swear by, yeah, you don't want to have it too close to the ground. You want to have it close to the antenna. It's got to be within that, 15 hundredths of a wavelength. And another guy in there's like, no, close to the ground. You can leave that lying on the ground. You can leave that lying on the ground. It works. So there's some experimentation that you can do here. So here I modeled this is your typical 80 meter DX dipole. It's a half wavelength. It is the frequency 3.9 megahertz. That's in the middle of the general phone band. Your length and your height are the same because it's a half wavelength and we want it to be a half wavelength above the ground. The takeoff angle, when I put it through NEC, came out to be about 30 degrees, gives you a 7.89 dBi gain. Your standing wave 2.7. So you probably think about something to either trim it or put in a match for it. But again, that is now a 30-degree takeoff angle. If we lower it down to a 1/10, we got same thing, frequency 3.9. The length is not going to change. I mean, we could trim it to get this SWR down, but that's not what I was going for here. But if we take it down to 1/10 of a wavelength, 3.66 meters, so we're talking, what is that? 9 to 20 feet, right around 20 feet. Your takeoff angle is 89 degrees. That's almost straight up in the air. And that's not too bad of a gain, 593.
It's about 10 feet. 9 to 10 feet.
Oh, yeah.
Yeah, meter is about a yard.
I don't know why I put the meters. I know I put the meters in it because I was pulling it right out of the computer. Yeah. Yeah. So 16 to 20 feet is what I have in the notes here because of I did the 8 and the 10. So, but yes. And again, you have to watch your SWR. That's outside of most radios' comfort zone. So you need to think about trimming it or putting some type of matching network on there. Do the exact same thing with the 40 meter. Here we are a half wavelength, almost 20 meters in height, 20 meters. Takeoff angles, 30 degrees, great takeoff angle, great gain, not too bad of an SWR. Probably going to want to trim it to get a better match. But when we go and drop that thing down to 1/10 of a wavelength, 9.85, 10 meters, 30 feet. I'm sorry, that's the length. Height. Yep. Yeah. I think I put that in wrong. Yeah, I'm missing a 1 there. Sorry, I did not have my proofreader for this. Because the approximate height of the half wavelength is going to be 20 meters. So it should be 2 meters. Yeah. So it should be about 6 feet off the ground, not less than a meter off the ground. But again, the takeoff angle, 88 degrees, 4.91 dBi, again, not too bad. Got to take a look at your SWR. Probably have a batching network or trim it a bit. And again, this one I just copied over those numbers, ignore those numbers, but this is the one where it actually has the reflector. So it has a parasitic reflector. I threw it in the NEC model, throwing a 5% longer. And I put this one to be a 100th of a wavelength off the ground. And you see, again, a slight bit of improvement. Okay, let me do that. Yeah, 491 to 507, was it? Yeah. So you get a little bit of improvement and not too much of a change in the SWR. So that can help you as well. Again, antenna consideration. You have to watch out for your ground losses. That's one of the things about having the antenna that low to the ground. Not only are you shooting the thing up into the ionosphere, you're also warming up worms, keeping the worms nice and toasty. You got to watch out for your SWR. You never heard that? I read it from a book. The guy's like, so the guy that wrote the Buddy Pole book talked all about that. He's like, yeah, unless you have the thing high enough up, you're just warming worms. And of course, you have to watch out for your SWR because, again, as your antenna gets lower and lower to the ground, your SWR goes higher and higher. So you need to change the length of it or put a matching network on there. And really, there's nothing magical about the inverted V and NVIS. Nothing. I mean, if you put an NVIS antenna high enough up, it's a great VX antenna. There's nothing wrong with it. There's nothing that makes that an NVIS antenna. I don't know where that perception came from. But my only guess is that because the ends of it are usually below, because it's inverted V, those are below your half wavelength, that you start getting some of that aiming up into the air. But there's lots of room for experiment. If you take a look in the literature, there's a whole lot of different antenna ideas out there with, multi-band antennas using different reflectors to try to aim your signal even better. So there's a lot that could be done in there.
Anything done to coils on the antenna itself?
Yeah, it's just an antenna. That's kind of my whole point is the key is knowing what your MUF is, so you pick the right frequency. I remember one NVIS day, Jerry specifically mentioned to me, he's like, they're scheduling an 80 meter net for this thing at 12 o'clock in the afternoon. The D layer is going to absorb it. And he was right. We didn't get any contacts in the 80 meter. The D layer was just too big. It was just absorbing at that frequency. So the whole key is, if you really want to do this, is know the frequencies that you need to communicate. What's your MUF between you and where you want to talk to? And again, lower the antenna. That's how you start getting those, things start aiming up. Your takeoff, your primary takeoff angle starts aiming up higher and higher and higher. That's what you're really going for. Yeah, yeah,
How much water should a person use on?
whatever is appropriate. One of the things you have to watch out for is that with this thing being low to the ground, you can start setting yourself up for RF exposure. So obviously you want to be, if you're going to pump 1500 watts through that thing and you're having it that low to the ground, you better mark off a nice area to keep people away from it. But I know with NVIS day, I think I talk a little bit about that coming up here. NVIS day for areas is 100 watts maximum.
Recording up there.
Yeah, you got to watch out. I mean, definitely with these antennas, this low to the ground, you start running into those things, some safety issues. So you do have to watch out for that. But yeah, NVIS day is Saturday, April 24th. Did I put that in wrong? It's the 23rd. Told you I didn't have my editor look at it. 10 a.m. to 4 p.m. Eastern Daylight Time. Try to communicate with as many participating Ohio stations. Try to talk to the Sarge up in Columbus. The exchange is simple. You need your 6-digit grid. That's not too hard to find out. There's 1,000 apps on the phone for that.
That 100, right?
100
Proofreading.
100 watts max.
Yeah, that's correct. It's not a typo.
No, they said 100 watts max.
Okay.
That's what they're trying to figure out with a barefoot rig. Your power and then a true measured signal report. So I don't know if there's what they're specifically looking for there. I mean, so Joe, you had a question.
I can't see the model.
Oh, yeah. The key to the models is the lower you down you go, your takeoff angle rises. So there's an inverse relationship to the height of the antenna and the angle. So with DX, you want to put that, the closer you get to a half wavelength, the more towards the horizon your signal is going to go. As you start lowering it down, the more your signal starts going up towards the vertical. And that's what we're trying to go for here. So that's really all those models were just showing examples of that.
Oh, okay.
That's all it was really showing. So, yeah, any questions?
So Saturday the 23rd is going to be Ohio NVIS Day.
Yeah,
And the plan or the goal of that is for people in Ohio to communicate to other people in Ohio via NVIS on either 40 or 80 meters. Is that correct?
Yep, sideband only. I don't think there was any.
Sideband voice. And is anybody here going to participate in that event with your club here or your group, or is no one interested in doing that this time? We have QCM is offering our site up in Finneytown, where we have our radio station and we have a large field area where we would welcome to have anybody that wants to come and join us and set up to experiment with their NVIS station and equipment and see how well they can do. There's enough room out there for many participants that would not interfere with others. If anybody's interested in attending, that with Cesi or myself or
Yeah,
Carl maybe, and see what some of those who will be there. There should be a room for you.
yeah, I can't participate, but I can forward on emails and try to help people as best I can. Yeah, it's interesting. I mean, it definitely works. I've used it before for Ohio Parks on the Air. You know, it's one of those where 40 meters, I'm getting stations on the outer edges. I'm getting Toledo, Cleveland, you know, maybe even like Steubenville and whatnot. I just can't get any of those close in ones. And near the end of the event, I said, fine, let's just roll out the rest of the antenna. So it's because there's a 40-meter link. Let's roll out the rest of the antennas in 80 meter. And the ends were practically touching the ground. And the top of it was probably 20 feet. I was surprised at how many contacts I was making on 80 meter at like 4 o'clock in the afternoon. I was in August. It was August. I was shocked.
That was from here in Cincinnati.
Yeah, it was a little further north up in near Lebanon.
Okay, and then if you change your height from 10 feet to 15 feet, could you calculate between if you were going to connect to Columbus or Cleveland? Or are you just, or you're just even wide enough at that height to cover the stakes?
So it was more a matter of, that was as high as I could get it to go. So I was more, not going more for NVIS, but just trying to get as many local contacts as I could. So Ohio Parks in the Air, you get multipliers for each unique park you get. My problem was I was getting a lot of out-of-state parks. I wasn't getting a lot of Ohio parks. So I didn't get a lot of multipliers. So next year, this year, I'm going to be definitely concentrating more on those, try to get those local contacts. So I'm going to be using an NVIS antenna to try and get some of those. I mean, we're in a better spot because really I just aim my antenna to the northeast. And I mean, the main lobe is pointing to pretty much the entire state. And again, I could get Toledo, Sandusky, Cleveland, Painesville, Akron, Canton.
Nothing closer.
But that's the whole problem is I need to use an NVIS. I need to start lowering that down. The problem is they need to do the same thing too. They can probably hear me, but they probably can't talk to me. Because again, the antenna, there's the whole game, but really this is more about sending your signal to the right spot. If the signal is coming down, you're going to catch it. If that's a DX signal, you're going to hear that DX signal. You'll hear Japan on 40 meter coming through, but you can't communicate with them because your signal is going up and then straight down. That's why you need the DX. So your antenna will catch it. So, do you have a question? Did you? Oh, okay.
As far as codes, I know that on field day, you got things like 3 alpha and 1 delta. Is that the same sort of procedure followed there?
For NVIS day, no. They just want to know your call sign, your grid square, and your 6-digit. Remember, it's just your 6 digits. Not EM79. It's EM79. Like my house is SB. Your true maiden designation. They're looking for your power, and then your signal report. And they want an accurate. They're trying to get an accurate signal report because again, they're trying to find out in an emergency situation what can they expect. If it's a statewide emergency, what can Columbus hear from Cincinnati? What can Okine and QCEN provide for emergency services in something catastrophic? That's really what they're going for. And also to make sure that clubs are prepared, that if something does happen and we are called upon to do something, that we have that expertise. So,
Hey, Cesi,
yeah.
give you an example. I checked into Ed's WinLink Wednesday last week using VARA over an NVIS antenna, 30 watts, 40 meters. The gateway was right on the Ohio River, right at Evansville, Indiana. So it was a perfect shot and only 30 watts to do it.
So how high was your antenna?
My antenna is it's supposed to be about 15 feet off the ground. It's kind of sagging right now after the winter. It's about maybe 12 in the middle.
So yeah, that's a great NVIS antenna. Yeah.
It's an MCOM2 by Chameleon.
So yeah, that's the other thing too. Just because you can't get your antenna high for the DX, yeah, you won't work the DX, but this will work all states. And again, that's one of those things. I find it's really hard to get my antenna set up at home on the higher bands to get Ohio, Kentucky, Indiana, West Virginia is impossible. You just don't see enough. Yeah. Any other questions? Any other comments? All right. Well, thanks for your attention.